Gravitational waves are pretty exciting. We've got this new way to observe the universe in an entirely new spectrum. It's like before we could see the universe and now we can hear the universe thanks to gravitational waves. And we've got the ground-based observatories like LIGO and Virgo and CAGRA, but there's a new space-based observatory under development called LISA, the Laser Interferometry Space Antenna. It's being developed by the European Space Agency. And it feels like it's just going to take forever. Like it's going to launch in 2035. But when it does, it will be able to observe colliding supermassive black holes, maybe be able to see the primordial gravitational waves of the universe itself, the aftershocks of the Big Bang. It'll be an amazing observatory to add to the collection. But what comes after LISA? Well, my guest today is Dr. Waldemar Martens from the European Space Agency, and he is proposing a version of LISA called LISAmax, and it would have arms that extend from the Earth-Sun L3, 4, and 5 Lagrange points, creating this gigantic equilateral triangle where each arm is about 250 million kilometers long, producing a gravitational wave observatory that is just ludicrously large. So I talked to Dr. Martens about the history of gravitational wave observatories, what is going on with LISA, and what LISAmax could do to take those observatories to the next level. Enjoy the interview. I've been following LISA for much of my professional career, and it feels like it's just unfolding in slow motion. It feels like it's never going to launch. And yet, and even now, 2035 is when we could see LISA. How is LISA doing? Is it going to happen?
I think it's more likely than ever that it's going to happen. As you say, there's a long history to LISA. It started like probably in the 70s were the first ideas. And then when it first became a project, a NASA project, and then it was canceled because of funding cuts. Because James Webb became so expensive and NASA had to decide, well, we have to take priorities. And so the LISA program was kind of canceled. And then it was resumed by ESA as a descoped mission, slightly smaller. But now it seems like we're almost back. Yeah, we're actually back to the original mission. It's just that it's under the lead of ESA and with NASA as a junior partner. So I think it's more likely than ever that it's actually going to happen.
And for people who aren't familiar, what will LISA be?
So LISA is a gravitational wave detector, which means that it's going to measure gravitational waves, which are similar to electromagnetic waves like light or X-rays or infrared light that we are much more used to in astronomy, but gravitational waves are a new type of way of looking into the universe. So to explain a bit what gravitational waves are, so they have been predicted by Einstein 100 years ago, and they were measured the first time in 2015 by LIGO and Virgo. These are two ground-based detectors. And gravitational waves are essentially ripples in the fabric of space-time. So to draw an analogy which is not perfect, but maybe sufficient, if you imagine water waves, if you imagine a perfectly still ocean and then you put two boats at a certain distance on that ocean, and then you see a water wave passing by, and then this water wave will cause the distance between the two boats slightly to change. So if they had a rope attached to each other, they would see that the tension of the rope would fasten and then go back again. And essentially that's what gravitational waves are to space, so to space-time. Space is not a fixed background as Newton was thinking, but it's kind of a flexible substance that can bend on its own. And gravitational waves are just propagations of these ripples of space-time.
And Lisa, like with the LIGO detector, I mean, we got those first detections of colliding black holes several years ago. We saw the kilonova, but there are the limits to what LIGO, even advanced LIGO, is capable of. What range of gravitational wave detections is LISA going to be capable of finding?
Yeah, so it's not so much that LIGO or LISA is that LISA and LIGO are competitors. They are complementary instruments. So LIGO is capable of measuring gravitational waves in the tens of hertz to several kilohertz range. So gravitational waves also have a frequency similar to sound waves or electromagnetic waves. And LIGO measures gravitational waves, if you will, in the audible range. So if we could make them audible, we could hear them, and that's what they actually do. They can hear the gravitational waves if they convert them to audio.
Yeah, I've heard that before. It's really cool.
Yeah, and that is related to the arm length of the detector. So LIGO works as a Michelson interferometer, which means that you have two arms which are arranged perpendicular to each other. The arm length is 3 or 4 kilometers. And that arm length determines the sensitive frequency range. So the larger the arms, the lower the frequencies you're able to detect. The smaller the arms, the higher the frequency. And these 3 or 4 kilometers arm length, they kind of determine the range that I mentioned before, so the audible range. And with LISA, we're going to space, and the arm length is much, much larger. It's 2.5 million kilometers. And that makes us sensitive to gravitational waves in the millihertz range, so much, much lower. So if you convert them to sound, you cannot hear them. It's really much, much lower. And that means that we're sensitive to also different sources, right? So you can imagine so the first detection of gravitational waves was a pair of black holes with around 30 solar masses. So they spiral around each other, and then finally they collide. And this collision is where the frequency is the highest, and that's what LIGO detected. But the larger or more massive the black holes or the source in general, the lower the frequency will be. And we know that there are supermassive black holes in the center of our galaxy and probably in the center of most galaxies, which have masses around or above 1 million solar masses, right? So LIGO, we were talking about 30 solar masses. Now we're 1 million or maybe up to 1 billion solar masses, which is just a huge, huge, huge difference. And we know that galaxies collide, and also these black holes in the center of those galaxies collide probably as well. And LISA would be able to detect those gravitational waves. So it is not that they are competitors, but they're really probe different frequency range, very similar to telescopes. There are telescopes for the visible range, for the infrared range, or for X-rays. So that's a similar concept.
But you mentioned that it will be capable of detecting gravitational waves with a frequency that is higher than LIGO is able to detect. But aren't those the gravitational waves from the merging supermassive black holes a much lower frequency? So does it go higher and lower than LIGO?
Did I say higher? No, it is lower frequency.
Okay,
yeah,
lower frequency.
So larger wavelength, lower frequency. Maybe if I
right into the hertz range, right? So then, you mentioned colliding supermassive black holes. Do we have a sense of how many of these are happening across the universe over any given time period?
I think there are estimates, but I don't know them by heart.
Right.
I think people do estimates on that, and I think the estimates vary also quite a lot. But I don't have a number in my head.
Right. But in theory, we will be able to detect them in a fairly large volume of space.
Yeah.
So
these are as I said, essentially galaxy collisions, right? So it's not that we expect such an event in our galaxy. So it's, by definition, it is something that is much further away.
What else could be detected with LISA?
So there are several different sources. So to me, let's say the most interesting or probably the most intriguing source would be detecting the gravitational wave background from the Big Bang. So just shortly after the Big Bang, so we are talking about fractions of a second after the Big Bang, there were processes that probably have created gravitational waves. So among these processes are inflation. I don't know whether probably you've talked about this in your videos as well. So inflation is a hypothesized period very early in the universe where the universe expanded exponentially fast. So really much faster than the rate that we're observing now. And this violent process could have created gravitational waves, and very similar to the cosmic microwave background that we observed that was created 380,000 years after the Big Bang. This inflationary period, or also other processes in the early universe, would create a background that comes to us from all directions in the sky very uniformly. And it's like an afterglow, not afterglow, but let's say ring after ring, or from the Big Bang.
Right. Yeah, like the first kind of scream of the universe.
Yeah, and the interesting thing is that it's, of course, much earlier than the cosmic microwave background. As I said, the microwave background was created 380,000 years after the Big Bang, and that has to do with the fact that before that time, the universe was opaque to light. So it was like a plasma, and every photon that would travel, it could not travel a whole lot. It would bump into an electron or a proton, or so it was not able to propagate for a long time. But then at a certain time, when the universe was cool enough and the distance between the particles was large enough, all of a sudden the universe became transparent, and that's where the microwave background was emitted, and that's what we measure today. But that was 380,000 years after the Big Bang. The gravitational wave background would be like fractions of a second after the Big Bang. And that would, of course, open up, would enable us to probe at a completely different scale the Big Bang. And that's kind of, for me, the most interesting thing that LISA could potentially detect. Whether it is able to detect that or not is still open, because there are many models for these processes. So I mentioned inflation, but there's also the electroweak phase transition, there's cosmic strings and whatnot. There are many models, and all these models have free parameters which you can tune, and depending on how you choose those parameters, you will create different signatures, and you will end up in a different frequency range or a different signal strength. And depending on where the reality is, where the universe actually chose to be, we might be able to detect it or not.
And I know that there was another mission that was considered, I've read a bunch of papers about it, that would be like a mega version of LISA. Not the LISAmax that we're about to talk about, but one that would be like 12 LISAs flying in formation, the Big Bang Observatory. And that would really try to nail down these primordial gravitational waves.
Yes, yeah. I don't know so much about this concept. I know that there was a paper, and the Big Bang Observatory is a frequently kind of studied observatory concept. That is, if I'm not mistaken, it will observe the universe in a similar frequency range as LISA. Because the size of the detectors are similar. But of course, I think there are 3 triangles, if I'm not mistaken, except so not.
I think it was 12 flying like a big 12-sided die, right? Like it would be sort of flying in a way that it would sort of be able to detect, as you say, yeah, 3 triangles, or maybe 4 triangles. Anyway, multiply that. So let's, I guess, what would it take to see the other end of the spectrum, like the ones that are really high frequency, the neutron stars orbiting around each other, the supernova that are exploding asynchronously, the even like maybe white dwarfs in orbit around each other? What would it take to go to high frequency?
On really high frequencies, we have the ground-based observatories, but there's in this intermediate range between LISA and the current ground-based observatories, there are also proposals that would be space-based, but with a smaller arm length. So detectors with a smaller arm length, and they could be even in Earth orbit because, you don't need to go to the place where LISA is with a smaller detector. There is a Chinese mission. I'm always confusing it. So there's Cain and Taiji, and one of them, of the two, is one of those smaller, targeting a higher frequency range.
And so, like, I know the advantage of putting your telescope in space is you don't detect trucks rumbling by, you don't detect seismic activity. So there's a lot of advantages to going to space, but that's interesting that you would have short arms, but in space, that would give you both that sensitivity, but also be focused on that very specific frequency range. It sounds like it would be a very productive realm of astronomy, because I mean, the thing that really excites me right now about gravitational waves and neutrinos is we're entering this era of multi-messenger astronomy, that we can see things in the electromagnetic spectrum, but also in gravitational waves and also in neutrinos, and you can kind of triangulate. It's as if you could see things and hear things and feel them at the same time.
Yeah, it's right. It's this era of multi-messenger astronomy that's what's currently really coming in. So, for instance, there's also this other mission called Athena, which you probably also, your listeners probably also know. So that's an ESA mission that is supposed to launch before LISA. But it would be really nice if that mission would have at least some overlap in mission time with LISA, because that would do exactly what you described. Observe the gravitational waves and the electromagnetic counterpart of the same events, potentially.
I mean, there are some mysteries in astronomy currently which are due to the fact that we kind of don't know the distances very accurately. Like, if we could get accurate gravitational wave observations of various things, what kinds of mysteries would we understand, do you think?
So that's not a topic that I work on myself. Let's say, so the areas of physics that we will be able to probe is, for instance, general relativity, the test of general relativity. Because black holes, or these supermassive objects that we study with gravitational waves typically, are really the area where so general relativity and quantum mechanics unite, in a sense, right? So quantum mechanics is the theory that describes very well all the phenomena at small distances, so the particle physics. And general relativity describes very well everything that is at large distances. So the history of the universe, stars, and but when you go to black holes, you put both theories to an extreme. So you have really very high curvature. So theoretically, in the center of black hole, there's a singularity, but we don't really know what whether that singularity really exists physically. But by studying these collisions of black holes, that is a way to really find out how these two theories could work together.
It's interesting. Like, I mean, it's like you're so focused on how do I build this thing? How do I make these detections? And you're going to let the theorists figure out what to do with the data.
To be honest, I would like to be involved in the in the data analysis as well. Right now, I'm more, as you say, so my main job is to be. I'm responsible for the orbit calculations of LISA, and slightly also I'm working on the contribute to the instrument side. But you cannot do everything at once, unfortunately. Yeah, because it's really such a rich field.
So let's talk about LISAmax. And so this, I'm always looking for not just what's the mission that comes next, but what's the mission that comes after the mission that comes next. And so when I saw like a proposal for an extension to LISA, I was pretty excited about it. And the ideas in your paper are pretty cool. So what would LISAmax be?
Yeah. So just to maybe provide some context, so the current program under which ESA does all the science missions is called Cosmic Vision, and LISA is in that program. It's the third mission in that third large mission in that program. But to look into the future, ESA is also looking what comes after Cosmic Vision. And so there was a call for proposals to the science community. What are potential missions that are worth looking into after LISA, after Cosmic Vision is finished? And among the selected science themes is also gravitational waves. And that's why the community is currently studying different potential successors of LISA. And LISAmax is a proposal that we put forward. That is a detector that aims at much lower not much lower, but lower frequencies than LISA. And to target lower frequencies than LISA, as I said earlier, we need even larger arm lengths. So LISA has an arm length of 2.5 million kilometers. If we want to increase that significantly, we have to change the way, so the orbits we put this observatory in, we need to find something completely different. And if you're into astrodynamics and you think about triangles, so LISA is a triangular constellation, the first thing that comes to mind to an astrodynamics specialist is the Lagrange points. So just to explain, so the Lagrange points
my
are
audience
equilibrium.
is so familiar with Lagrange points. Like it is
okay, good, yeah.
Almost every question that I get has Lagrange points in it, but specifically, which Lagrange points are you looking at?
Yeah, so there are the triangular Lagrange points L3, 4, and 5. So those are at 1 AU from the sun, same distance as the Earth, but they are, so the three Lagrange points form an equilateral triangle. So that's exactly what we want for a gravitational wave detector. And what is also nice about those points is that the dynamical environment is very quiet. So there's no big bodies in the vicinity. If you put something there, it will stay there more or less.
So sorry. So if you put something in the Earth, Sun, L4, L5 Lagrange points, those are the ones that are ahead and behind Earth in orbit, and then something at the L3 point, which is on the other side of the sun from the Earth, you get an equilateral triangle between those 3 points.
That's right.
Right.
Yeah.
Wow, like a use for the L3 point. I don't think anybody's ever thought of that yet.
Yeah, so to correct maybe a bit, so I said if you put something there, it stays there. It's not exactly true for the L4 and L5 point because they're, strictly speaking, unstable. So over a long time, it will drift away, but the time scale is really, really long. So, And then there's another problem with L3, as you said, you didn't know there's a use for it. And actually, it's not so useful because it's behind the sun as seen from Earth. And how do you communicate with a spacecraft that's behind the sun? And that's why we didn't choose those points exactly, but we shifted the triangle by 5 or 10 degrees. So you can either works, 5 or 10 degrees. And it turns out that it is still rather stable. So it's not that because you move the triangle, you rotate the triangle, that you completely lose that stability. In fact, if you optimize the orbit and then look at the stability of the triangle over a mission duration of 10 years, it's even more stable than LISA. So just to give you an idea.
Wow. Like comparatively speaking, with 150 million kilometer arms, or however long the triangle arms are, you've got it just like compared to LISA with its 2.5 million, you are more stable.
Yeah, I have to define what more stable means. So more stable means when you measure the corner angles and look how they evolve over time. And for LISA, the corner angles typically evolve plus minus 1 degree. So 60 degrees plus minus 1 degree over the 10 years. That's because we have the Earth perturbation and you cannot achieve a perfectly equilateral triangle. So you have the corner angles change over time. With plus minus 1 degree for LISA and for LISAmax, we achieve less than 0.1 degree of variation over 10 years.
So 10 times better in sort of less variation of your triangle.
Right.
And like with L4 and L5, I mean, they're stable. I mean, we see objects trapped in the Trojan regions of the Earth's orbit. We see it in Jupiter. So, but they are, I always describe them as they're like big blobs. They're affected by the gravity of the Earth, the gravity of the Moon, the gravity of Jupiter. Like they're not points. And so they're regions that you orbit within. While the L3 one, you're going to be drifting and you're having to constantly add propellant to bring yourself back into position. So I guess which of these three is the most difficult to manage your spacecraft at?
You don't have to correct the orbit actually for L3, neither for L3 nor for the other two. So it turns out if you consider so you have to fine-tune your initial position. That's right. But if you manage to put your spacecraft at a precise point, then you don't have to. So it is stable. What we haven't investigated yet, how does that stability deteriorate if we, in reality, are not able to put that exactly at the computed point? So that's something that hasn't been analyzed in our paper. But it has been done for LISA. So for LISA, we did that analysis, and the let's say the dynamical environment for LISA is much closer to Earth, so it's much more dynamic. And if it works for LISA, we would expect it would also work for LISAmax.
And if you've got 10 times the room to play with, then that gives you a chance to have this all unfold a little more slowly than it does in the case of LISA.
Right, yeah. And I have to mention another thing. So I mentioned the breathing of the corner angles, but there's another measure of stability which is important, and that's the relative velocity between the spacecraft. So the velocity along the connecting line. So that's where the laser will be going along. And why is that important? So what a gravitational wave detector measures is a change in the distance, a tiny change in the distance between the two spacecraft or the two test masses that are in the spacecraft. And we don't have a fixed triangle in space. It will always move because of the orbital dynamics. There will always be a velocity between the two. And that's not a problem per se, but we have to limit the range in which the velocity is allowed to be, because otherwise the beat nodes that are detected in the interferometer get out of range of the phase meter. So the phase meter, the instrument that measures the signal. So when you interfere the two lasers, the beat note that's created, that's measured by the phase meter, and that for LISA can only measure between 5 megahertz and 25 megahertz. And if your relative velocity becomes too high, the signal moves outside that band. And so that's something that we have to also watch carefully. And for LISAmax, this relative velocity is for the baseline constellation, let's say, is also lower than for LISA. So it's for LISA we have plus minus 10 meters per second velocity variation amplitude, let's say. And for LISAmax we have plus minus 3 meters per second. So again, a factor of 3 roughly better.
Right. That's exciting too. But you are looking at much longer time for the laser to get from spacecraft to spacecraft, like on order of more than 10 minutes.
Yeah.
What does that is? Can you still interfere the laser signals with that kind of a time delay?
Okay, there's the answer is probably yes, because the time delay is so maybe go back to LISA once again. Even in LISA, we don't directly interfere the signals from two arms. What we actually do is we detect or we measure each arm separately, and then on ground we do what's called time delay interferometry and kind of do the interferometry on ground by digitally combining the two lasers. And why do we have to do that? And the reason is that, again, the arms in the interferometer are not fixed. So if you're on a ground-based detector, the arms are fixed, and if you choose them exactly the same length, you are sure that when the laser travels both ways, comes back, and then interferes, it is coherent. So it will interfere, and all the laser frequency noise that is in every laser will cancel out, because it has traveled the same distance. But if your laser arms are not exactly the same, which is the case for LISA, so because the arms are varying over time, you don't get this cancellation of laser frequency noise. So that means that if you did the same thing as you do on ground, you would actually have a noise in your signal that is much, much higher than the gravitational wave signal that you would like to measure. And there is this ingenious concept that was proposed like 20 years ago, which is called time delay interferometry, where you, as I said, you record the signals individually of the laser arms, and then you delay one of the signals by a certain amount, which is determined by the current distance between the spacecraft. And if you do that right, then you still get this cancellation of laser frequency noise. So that all that is to say, you in any case you have to delay your signals and interfere them on ground. So if for LISAmax you then go to you have a much larger travel distance, so you have a natural delay in your signal path. It's not expected to cause any additional problems.
So, I mean, when I think about, say, the very large telescope here on Earth, they're having to interfere the signals from the different telescopes in real time because it's a very small wavelength. They're viewing in infrared. But when you think about, say, the Event Horizon telescope, where you had in radio waves with these telescopes all around the world, they were able to just record their data with a very accurate clock and then merge the signals on supercomputer. So with both LISA and LISAmax, you would be recording the signals and then merging them on supercomputer afterwards to tease out the data.
I don't think it will require supercomputers in the case of LISA or LISAmax. I think the Event Horizon, that's an example. So I guess it is a much more complex scenario that you have there. I think the data analysis that has to be done for LISA can probably be done on a smaller computer. So it doesn't require any super high fidelity number crunching. Yeah.
Okay, that's good. That's exciting. So then, this is sort of like all of the technical issues on getting to this telescope. So what does this get us? We've got this telescope that is forming an equilateral triangle between the 3 Earth, Sun, Lagrange points. You are with just enormous arms. What kind of a gravitational wave observatory have you built with LISAmax?
Yeah, that's the big question. Is it useful or is it not useful? Right?
Yeah. Do we need this?
Yeah. Yes. Yeah.
My default answer is yes. We need this. Bigger is better with telescopes.
Yeah. It's not a given that it's useful, and that's why it's not the only frequency range that is studied. Currently, the scientific community is studying 3 different frequency ranges. One is the one of LISAmax, so below LISA. One is millihertz, so roughly the same at LISA, but better sensitivity. And the other is decihertz, so higher than LISA. And the goal of this exercise is to determine which of those 3 frequency ranges actually has the better science case. Which do we want to propose actually to ESA and to build in the end? And of course, to do the decision, we would like to have the LISA data because right now we don't actually have a lot of information about gravitational waves, right? But as it seems, the investigation has to be done before LISA flies, of course, because LISA will fly in 10 years, and more than 10 years. So to give you one example of a possible benefit or a possible science case of LISAmax is we talked about these large supermassive black holes in spirals. Since LISAmax is much more sensitive at lower frequencies, so around 2 orders of magnitude more sensitive at the microhertz, in the microhertz range than LISA, it will be able to detect these signals from the supermassive black hole in spirals much, much earlier, so like thousands of years before they actually merge. And if you observe such a signal over a much longer time, you will be able, of course, to measure certain parameters much more precisely than you were able with LISA. And probably there are many, many other science cases which I don't know about, and we're just trying to find out. So to me, it's not about justifying that we have to build this observatory, but to find out really what is the most interesting frequency range and what has the most compelling science case, and that's the one that should be proposed.
And I know that there have been some pretty exciting discoveries with the pulsar timing network to detect a background gravitational wave signature to the universe from all of the various gravitational wave events that are happening. Would LISAmax help you get a better sense of that background gravitational wave signal?
So the pulsar timing arrays are, again, in a much, much lower frequency range. Even compared to LISAmax, it's much, much lower. So it's, I can't say a number now, but it's like probably 3 orders of magnitude lower or even more. So it is very hard to say because, as I said earlier, depending on the model that you choose, you will get a signal in a different frequency range, and it's possible that you can detect it with a pulsar timing array, but not with LISAmax. It's possible that you can detect it with both. It's very difficult to say.
No, but it does sound like you've got a spectrum of gravitational waves, with the pulsar timing array being at the very limit on the large end of the spectrum, and then you've got these short-armed space telescopes that are finding the really quick ones, the white dwarfs circling one another. And then you've got sort of this nice range in between, from ground-based observatories like LIGO to space observatories like LISA and then LISAmax, filling in that gap between the pulsar timing array and LISA.
Yeah.
And as you say, you might get to a point with LISA where they're just like, oh, we almost saw a hint of primordial gravitational waves. I wish there was a way we could see more. And then, you just sort of put your paper in front of everybody again and wait. I mean, okay. And I know you can't say this, but it sounds to me like LISAmax might be a better idea than LISA. Is that possible? In that it solves a bunch of problems that LISA has had to be engineered for. Could it do the work of LISA and minimize some? What's the big downside of LISAmax?
It's not clear that it's better in all respects. So first of all, as I said, it's again a different frequency range. So in that sense, it's complementary. It doesn't replace what LISA does, because also, maybe I haven't emphasized it before, it is more sensitive at lower frequencies, but that gives a penalty at the higher frequency. So you're less sensitive above 1 millihertz. LISA is more sensitive in that range. So you might miss out on that frequency spectrum. And there's another issue that is currently being investigated, which we have with LISAmax, but not for LISA. So the LISA detector, it's a triangle and it rotates. So it moves around the sun once per year. And as it moves around the sun, it also rotates around the constellation center. And also because it's inclined by 60 degrees relative to the ecliptic, over the year, the triangle changes the orientation and kind of sweeps out the sky. And because the detector has an antenna pattern, so very similar to an antenna pattern of a radio antenna, it's more sensitive towards one direction and less sensitive to other directions. When you sweep out the sky, you get to see different locations in the sky, one thing, and the other thing is that allows you to localize the source. So how does that work? With LISA, it works by observing one source over an extended period of time. So let's say you observe one source in a given direction, and at a given point in time, it enters a certain part in the antenna pattern. At a later point in time, it will hit a different point in the antenna pattern where the signal is lower. And if you record the evolution of the signal strength, you get a certain signature over 1 year. And if you look at the source in a different direction, that signature will be different.
I understand. So in that LISA is, when you see the animations of LISA, it looks like this kind of tumbling triangle that's moving in orbit around with the Earth as it's going around the sun. And so depending on the configuration, both of that triangle as well as where it is on that orbit around the sun, you're getting to look at this same object at different times in different ways. And if it's taking a little longer to unfold, then you're getting really precise measurements where you're taking advantage of the different configurations of the spacecraft.
Not only that, but also you're able to tell where is the source, because the position in the source determines the signature of the signal strength, of the amplitude of the signal. And so you have this sky localization capability with LISA, and since you don't have this precessing motion with LISAmax, because LISAmax is confined to the ecliptic plane, it only rotates as a whole around the sun, but in one plane. And so at this point, it is not clear, are we able to localize objects as well as we can do for LISA? And that is a big issue if we cannot do that.
I remember when LIGO first came online, they could tell whether the signals were coming from this hemisphere of the sky or that hemisphere of the sky. And it wasn't until the Virgo Observatory came online in Europe that they were able to add a much more precise three-dimensional picture of where the source of these events.
Yeah, I think they do it kind of a bit differently because they use a sort of triangulation, because then they have two detectors and then the wave arrives at different times and then that gives them some information. Yeah, and it is, of course, important to localize the source. First of all, because if you know where the source is, you can tell the electromagnetic observatories where to point. And also it gives you it lets you distinguish different sources. So for instance, if you measure a gravitational wave background that comes from all directions uniformly, localization capability enables you to distinguish that from a very localized source, of course. So it is important to have that capability.
My audience is quite fascinated by the idea of interferometers, and mostly it's about making really big telescopes. Could this orbit configuration be used for other wavelengths? Could we create a version of the Event Horizon Telescope that is recording in radio waves from those three positions as opposed to gravitational waves?
That would be a completely different concept. I mean, the whole setup of the... So you mean putting three radio telescopes on these three positions?
Mm-hmm. Recording data, sending their data home to Earth, having a supercomputer crunch it, having a having a baseline that is 100 and I don't know how long are the arms? I'm trying to think, do my math here.
259 million kilometers.
There you go, 259 million kilometer baseline.
Yeah.
Is there value there? Is that possible?
Okay. I'm not familiar with the radio telescopes, but I guess what will be an issue is the size of the telescope that you need to put there, right? They have to be much larger than what we need for a gravitational wave detector. Mm-hmm. And large telescopes mean, of course, high mass, and that's expensive to launch into space. I guess that's the primary issue, but I'm not an expert on the.
But I guess like that drift that's coming between the three telescopes rule out any kind of real-time interference between the signals. Like you couldn't do what they're doing with, say, the Very Large Telescope, where you are interfering the signals from each other to make a telescope that is 259 million kilometers across. Like you're not going to get interferometry unless you do it.
I mean, I'm not familiar enough how they do it with the Event Horizon Telescope. I mean,
very accurate clocks, and then they number crunch it, right?
Yeah, you have a drift with if you have this triangular constellation, but maybe if you know precisely how the drift is, how you can predict everything very precisely, and you can estimate the clocks on board very precisely, maybe that information is sufficient to still use that. But I'm speculating.
Now you had mentioned earlier on that you had sent in this proposal as part of the Cosmic Visions. Was it the 2050 call?
It is called. It's called Voyage 2050, but it doesn't mean that it is for 2050. It is covering the time frame between 35 and 2050. Yeah, it's just in the name.
No, I've mined that Cosmic Visions 2050 over and over again because there's such great ideas in there. So what's next? I mean, you've delivered your paper. Is it just going to, you've sort of thrown it out there and you're going to get back to work? What do you hope happens next?
So the paper is not a proposal yet. It's just a paper. It's published like any other paper. We're currently working with the LISA consortium. So there are currently 3 working groups in the consortium who study the 3 different frequency bands to come up with a concept and a proposal to ESA. That would be an actual proposal. And the LISAmax is an input for that. And we hope that a lot of the work that has been done for LISAmax we can use for that proposal as well. But as I said, the actual proposal will come hopefully beginning of next year. And then typically what happens in ESA is when the proposals are done, some of the selected proposals go into the concurrent design facility, the CDF. So that is a concept to study a mission, a feasibility study, which within a limited time frame of typically 2 months, where you sit together with all the different experts from all the different subsystems of the spacecraft. So the configuration, the propulsion, the thermal, the trajectory, everybody who's involved in the mission design, and you come up with a overall concept for the mission, and you identify potential showstoppers and challenges, and you do cost estimate, and that's probably what will then happen if one of those proposals is successful. And I have to also say that so that proposal would go into the L6 slot, so that would be a large mission, L, and 6 for the 6th large slot. And the theme of that slot is not only gravitational waves, but also it's in general the early universe. And so we would compete probably with proposals from the cosmic microwave background community. So,
well, Dr. Martens, good luck with this. It's an exciting concept, and it would be wonderful to see those signals from the beginning of the universe itself. That would be quite exciting.
I agree.
All right. Thank you so much.
Thank you very much for having me.
A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Vlad Shipolin, Jay Dennis, David Giltanen, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.